Dear students, continuing our lecture series on organic reaction mechanism. This is our 12th lecture, and in the previous lecture we have done basic concepts on carbenes, and in this lecture we will be discussing about reactions of carbenes. Carbenes, as you know, they are electrophilic in nature, and because of the electrophilic nature of carbenes, they generally undergo addition or insertion reactions. The most common reactions among the carbenes, they are cyclopropanation reactions, insertion reactions. Then, being an electrophile, they can combine with a nucleophile. So, combination with a nucleophile, these types of reactions, they also undergo. Then, they can also undergo rearrangement reactions. Then, ring expansion or ring contraction reactions, and then some other reactions like dimerization reactions or Reimer reaction, which is a common example of carbene reactions. And the first is cyclopropanation reactions. So carbenes, as we know that carbenes, they are of two types, singlet carbenes or triplet carbenes. So depending upon the type of carbene which is involved, the carbenes, they add to the carbon-carbon double bond to form cyclopropanes, and this reaction is known as cyclopropanation reaction. And these reactions, they are very fast and exothermic in nature. Now, but singlet carbenes or triplet carbenes, they react differently with the alkenes. When singlet carbenes, they are added to alkenes, then the reaction will take place in a concerted manner, and this reaction will be a stereospecific reaction. For example, if we see the structure of the singlet carbene, we know that the two electrons present which will be forming a bond with the alkene, they are anti-parallel in nature. And similarly, these two electrons which are forming the pi bond, they are also anti-parallel in nature. So that means the bond formation between this carbon and the carbon of the carbene can be a concerted effort through this type of transition state. And that is why, because this reaction is a concerted reaction, we are getting only a specific isomer out of the various possibilities. So that is why this reaction is a stereospecific reaction, and we will exclusively get only one isomer. So singlet carbenes, they are stereospecific in nature. Then is triplet carbenes. In case of triple carbene, we know that both the electrons, they have the same spin. They have parallel spin. So that means out of these two electrons of the pi bond, this can interact at once only with one of these electrons. So these carbon-carbon double bond will interact with any one of the electrons to form a carbon-carbon bond. This carbon and say this carbon of the carbene. So we will get first this type of transition state where both these electrons, they will have the parallel spin, and because they are having the parallel spin, that means they cannot form a carbon carbon bond until one of them, they are anti-parallel in nature. So there are two ways of making these electrons anti-parallel. One is that in a slow step, the spin inversion at the carbene carbon can take place, and when spin inversion takes place over here, now these two electrons, they have anti-parallel spin, and that is why formation of the carbon carbon bond takes place, and we will get this type of isomer when the product is formed through this route. Then second route is that this carbon-carbon bond being a single carbon-carbon bond, this can very easily undergo carbon-carbon bond rotation. So rotation of the carbon-carbon bond will take place. So we can see over here, H is beta, R is alpha. So by rotation, H will become alpha and R will become beta. And then this carbon can undergo spin inversion, and now we have anti-parallel spin, and then this can cyclize to another type of isomer. So the triplet carbene will react in a stepwise manner. So either through this step or through this step, and they will act like a biradicals. So both the electrons, they will not react at once, but they will react one by one. So that is why they will give a mixture of isomer. Hence this addition of triplet carbenes to alkenes is a stereoselective reaction rather than stereospecific reaction. So in case of singlet carbenes, we will get stereospecific product, that is only one isomer will be formed, whereas in case of triplet carbenes, we will get stereoselective product, that a mixture of both the isomers that will be formed. So the reaction is a stepwise reaction, and the product is formed through stereoselectivity. Then cyclopropanation can take place either intermolecularly or intramolecularly. So example of intermolecular reaction is, say we are having this type of alkene bicyclo-2,2,1 heptuene, and if we react this with some diazo compound, we know the diazo compounds, they will very easily give us the corresponding carbene. So here carbene will be formed by the removal of one molecule of nitrogen. So this carbene will add to this carbon-carbon double bond to give us these types of cyclopropanation products. And because this reaction is taking place between two molecules, so that means this reaction is an example of intermolecular cyclopropanation reaction. Similarly, if we are having this type of trans substituted alkane, on one carbon we are having this heterocyclic moiety N-methyl pyrrole, and on the other side we are having this ester group. So if we react this with diazomethane, we know in presence of lead acetate, this will give us a carbenoid where this CH2 will add to this carbon-carbon double bond, and this type of cyclopropyl derivatives, they will be formed as the product. And again these two molecules, they are there where reaction is taking place, hence this is also an example of intermolecular cyclopropanation reaction. Now you see this molecule here, the diazo compound as well as the alkene part, they are present in the same molecule. So when this is reacted with rhodium acetate, then we know that this diazo part will react with rhodium acetate to give us a carbenoid, that is metal carbene complex will be formed at this place, and that metal carbene complex will add to this carbene-carbon this carbon-carbon double bond to give us cyclopropanation products. So this is how the same molecule which is having both the reactants, the carbene part as well as the alkene part, they will undergo this reaction to give us the cyclopropanation product. So this is an example of intramolecular cyclopropanation reaction. Then is a very important reagent which is used for cyclopropanation, that is Simmons-Smith reagent, and this is very commonly used for cyclopropanation of alkenes. This reagent consists of diethyl zinc and diisoiodide. So copper, zinc and iodine, they form the active reagent which is called as iodomethyl zinc iodide. So in actual, when these two they react with each other, diethyl zinc and diisoiodide, then we will get iodomethyl zinc iodide as the actual reagent which participates in the reaction with the alkenes for cyclopropanation reactions. And this is not a pure carbene, but this is a carbenoid, that is metal carbene complex is formed, and this metal carbene complex then adds to the carbon carbon double bond through this type of transitions. So methylene part will add to the carbon carbon double bond, and then zinc iodide will be removed from here, and we will get cyclopropanes as the product. And the addition take place in a syn manner, because this will add only from the one side of the molecule. So we will get syn products through this type of cyclopropanation reaction, that is Simmons-Smith reaction or Simmons-Smith reagent will give us syn products of cyclopropanation. So again, this is one more example of Simmons-Smith reagent. Here you can see that there are two carbon-carbon double bonds, and the Simmons-Smith reagent adds selectively on this carbon-carbon double bond and not on this carbon-carbon double bond. The reason is presence of this group, uh, trimethylsilyl group, which is present, and because of this oxygen an intermediate is formed in such a manner that this carbenoid preferably adds to this carbon where this group is attached. And also, if we are having ortho hydroxyl group or any other group which is having oxygen, that carbon carbon double bond is preferred by such type of reagents for cyclopropanation, whereas terminal this carbon carbon double bond will be not affected for cyclopropanation. So we can see that such type of cyclopropanation can be told as a selective cyclopropanation reaction, because these double bonds they are not affected by this reagent. Then some carbenoids like dirodium tetrakase S is for optically active isomer of this, and do-decyl benzene sulfonyl prolinate. This is abbreviated as RH2SDUSP. This is used effectively as a catalyst for these types of cyclopropanation reaction, where we get enantioselective products. So here what happens is that this reaction is useful even for terminal alkynes also, where most of the cyclopropanation reactions we have seen the examples of alkenes only, whereas this reagent can be used for enantioselective cyclopropanation reaction between terminal alkynes and aryl vinyl diisoacetates. So these are aryl vinyl diisoacetates, and these are second substrate, that is terminal alkynes. So when we react these diazo compounds with these types of optically active rhodium complexes, then we will get carbenoid here with the removal of nitrogen gas, and two molecule will be removed, and here we will get carbon metal complex. A metal here is rhodium. So metal rhodium, carbon rhodium complex as a carbonide will be formed, and that carbonide will add to the carbon-carbon triple bond in an anisotrophic fashion to give us these types of cyclopropene derivatives as the product. And you can see that here we get only anisomeric products, and the reaction is anisoselective in nature because the catalyst which we are using is a chiral catalyst. Then second type of reactions, they are insertion reactions. They are very common type of reactions which take place in case of carbene chemistry. The insertion reactions, they may or may not occur in a single step. So they may be taking place in a concerted manner, or they may take place in steps. So either they can be concerted or they can be stepwise. And general order of preference for insertion of carbene is to the carbon hydrogen bond, and then second preference is XH bond, where X may be any atom other than carbon, maybe halogen or oxygen or sulfur. So all other types of bonds, they are also preferred for insertion reaction. And third preference is for the carbon-carbon bond, which is very low possibility, and but most common is carbon hydrogen bonds. And general characteristics of these insertion reactions is that they may be taking place intramolecularly or intermolecularly. So whenever there is a possibility of an intramolecular insertion reaction, then no intermolecular insertion will take place. So if there is no possibility of intramolecular insertion, only then intermolecular insertion will take place. And rate of intramolecular insertion is always faster than the rate of intermolecular insertion reaction. And insertion reactions, they will take place generally in rigid structures. Rigid structures, they will favor such type of insertion reactions. Then in case of flexible structures, if there is a possibility of formation of either say 5-membered ring or 6-membered ring, then the formation of 5-membered ring will be preferred over the 6-membered ring formation because of the thermodynamics. So 5-membered rings formed, they are more stable as compared to 6-membered ring formation, because the transition state which is formed during the insertion, that is thermodynamically more stable when 5-membered ring formation takes place. And the both inter and intramolecular insertions, they undergo asymmetric induction when we use chiral ligands on metal centers. Then mechanism of these reactions, as I have told you, that they may take place in a concerted manner, that is one-step mechanism or two-step mechanism. One-step mechanism is that the carbene adds to this carbon-hydrogen bond in a single step through this type of transition state. So this adds simultaneously to both the carbon hydrogen bond, and when this bond breaks, then only the final product is formed, but the whole process takes place in a one step. Whereas in two-step mechanism, the carbene first interacts with the substrate with the removal of H radical from here, and we will get this alkyl radical or and this methane carbene will be converted into methyl radical, and then two radicals they will join together to give us the product. But this reaction takes place in two steps. In the first step, these radicals are formed, and then in the second step, these radicals they join to form the product. The first step is the slow step, whereas this step is a fast step. Then when methylene carbene is there, then the insertion reaction competes with the cyclopropanation reaction in case of alkenes. So for example, if we are having say this trans-butene, and we react this with methylene carbene generated from diazomethane, so then two types of reactions can take place. Either this methylene carbene can add to this carbon-carbon double bond, or an insertion reaction can take place either at this place or at this place. So likewise, if cyclopropanation takes place, we will get this as the product, and if the insertion takes place at either this methyl or this methyl, then we will get this type of product. Whereas if insertion takes place either at this place or at this place, then we will get this type of product. But insertion preferably, if insertion is to take place, that will take place either at this methyl or at this methyl, because 40% of the product formed through insertion is at this position, whereas minor insertion product is formed when this is inserted between this carbon and this hydrogen. But we can see that the major product in this case in comparison to these two is the cyclopropanation. So cyclopropanation competes with insertion reaction in case of alkenes. And then as we have seen some examples of carbene, there are carbenoids also which can undergo intramolecular or intermolecular insertion reactions in case of CH bond insertion. So for example, this is the example of an intramolecular insertion reaction. This is a diazo compound you can see over here, and when this will be refluxed with copper in benzene, we know a molecule of nitrogen will be eliminated and carbene will be formed at this place. And this carbene can undergo an insertion reaction at this place, this carbon hydrogen bond, and we will get these types of cyclopentane derivatives as the product. And this reaction, you can see that this is a stereospecific reaction, that this will add only from one side of the molecule, and that is why we are getting only a stereospecific isomer. Then the examples of intermolecular insertion reactions in case of carbenoids. This is adamantane, another tricyclic hydrocarbon, and this carbon hydrogen bond will undergo insertion reaction in the presence of these types of diazo compounds, and this rhodium compound is used as the catalyst. Dirhodium tetrakase SN-2-decyl benzene sulfonyl prolinate is used as the catalyst, and you can see that this is a chiral catalyst, and that is why insertion is also enantioselective insertion, in this case we will get an enantioselective product. So when this catalyst reacts with this, with the elimination of nitrogen molecule, we will get this type of carbenoid, and that carbonyl will undergo insertion reaction at this carbon hydrogen bond to give us this type of enantioselective product, where the insertion around this carbon hydrogen has taken place. Then second example, same catalyst, if these diazo compounds they react with cyclohexane, then also we can get these types of products. And because these are not the chiral carbons, so that is why we will get a product of this type. Methyl cyclohexyl phenyl acetate will be formed as the product with the addition of the carbenoid generated from this diazo compounds and this chiral catalyst. Then is some more examples, alkylidene carbenes, which are generated from trimethylsilyl diazomethane on reaction with these types of ketones. They will react with each other to in presence of n-butyl lithium and tetrahydrofuran THF as the solvent. So we will get these types of alkylidene carbenes as the intermediates, and these carbenes they will undergo carbon hydrogen insertion reactions at this place to give us these types of five-membered cyclic alkenes as the product. And this is very important reaction for the conversion of carbonyl compounds into alkenes. One more example, this type of 1,3-diketone diazo compound, which is 8-membered cycloocta 1,3-diketone. When this is reacted with rhodium acetate, we know that with the removal of a molecule of nitrogen, we will get a rhodium carbenoid complex at this position, and then this carbene will add to this carbon hydrogen bond, and insertion reaction will take place to give us these types of diketones as the product. And why this carbon hydrogen bond insertion take place not at this or this? Because if here the insertion will take place, we will get a 6-membered ring and a 4-membered ring. And as I have told you, whenever there is a possibility of intramolecular insertion, the 5-membered ring formation is preferred over 6-membered or any other member, that is either 6-membered or 4-membered. Then only 5-membered ring formation will be preferred. So that is why the insertion takes place at this carbon hydrogen bond. Then similarly, the insertion can take place at nitrogen hydrogen bond or oxygen hydrogen bond, but that is preferred. Preference is less as compared to carbon hydrogen. And some examples of insertion in nitrogen hydrogen and oxygen hydrogen bonds are this, that when these types of diazo compounds they are reacted with, say, piperidine in presence of copper bronze at 45 degrees centigrade, then NH insertion will take place. So we know that the carbene will be generated at this place with the elimination of one molecule of nitrogen, and this carbene will add to the this nitrogen hydrogen bond, and we will get these types of products through NH bond insertion. Similarly, these diazo compounds, they can also undergo OH insertion, that if instead of piperidine we use methanol, then insertion around this oxygen hydrogen bond will take place and we will get these types of ketoethers as the product. Then as you know that carbenes, they are electrophilic in nature, and because of that they very readily combine with any nucleophile to give us a stable product. So one example of such is the reaction of carbenes with sulfur compounds to give us sulfur ylides, and these sulfur ylides, they undergo intramolecular nucleophilic substitution to give us the rearranged products. So for example, if we are having this type of diazo compound, uh, when this is reacted with rhodium acetate, we will generate a rhodium carbene complex at this place with the removal of one molecule of nitrogen, and this will add to this thiophene which is present as a solvent, and we will get this type of sulfur gelate. And when this sulfur gelate is refluxed for 2 hours, then intramolecular nucleophilic substitution. So this negative charge act as a nucleophile. This attacks at this carbon, and we will get this type of product. So you can see over here, this attacks as a nucleophile at this carbon. This bond shifts to this position, this bond shifts to this position, and this bond is broken. Carbon sulfur bond is broken, and we will get these types of intermediates. And then rearrangement of removal of H positive from here will lead to the formation of products through resonance. So this is how carbenes, they react with nucleophiles to give us rearranged products through intramolecular nucleophilic substitution reaction. Then some other examples of rearrangement reactions. Alkyl carbenes, they can undergo rearrangement reactions which involve either 1,2 or 1,3 hydrogen shift, or 1,2 or 1,3 alkyl shift, or even phenyl shift. So all these types of reactions, they will give us rearranged products. Rearranged means the normal product which was possible will not be formed, but instead a rearranged product will be formed. So for example, if we are having this carbene, and if it undergoes this type of shift, that this hydrogen along with pair of electrons is shifted to this place, and this bond is used to form a carbon-carbon double bond, then we will get these types of alkenes as the product through 1,2 hydride shift. Similarly, this type of molecule can undergo 1,3 hydrogen shift also, and if 1,3 hydrogen shift takes place, then a formation of carbon-carbon bond will take place, and we will get these types of cyclopropane derivatives. So either we can get alkenes as product through 1,2 hydride shift, or we can get cyclopropane derivatives through 1,3 hydride shift. Then an important reaction, that is Wolff rearrangement. This involves carbenes as intermediates in the reaction, and these carbenes, they are generated from diazo compounds. They undergo 1,2 phenyl shift to give us the final products. So for example, if we are having these types of alpha diazoketones, we know that these diazo compounds will undergo elimination of a molecule of nitrogen like this, and then these types of carbenes, they will be formed, and these carbenes, they will undergo 1,2 phenyl shift. So this will form a carbon-carbon double bond. This phenyl is shifted to this place, and we will get uh, diphenyl ketenes as the product. And these ketenes, we know they are very useful in organic synthesis, that they can interact with many types of say nucleophiles or some other reagents to give us different types of organic products, which are very important for organic synthesis. Then carbenes, they can also undergo ring expansion reactions when they are reacted with aromatic compounds. And these aromatic compounds may be carbon-carbon aromatic compounds or heterocyclic aromatic compounds also. For example, if we are having this diazo compound, and when this is heated or on photochemical radiation, we know with the elimination of molecule of nitrogen, this will give us this type of carbene, and this carbene will add to the carbon-carbon bond of the aromatic compound in the presence of some metal catalyst, and we will get these types of intermediates, and these intermediates, they will undergo ring expansion reaction to give us this type of 6-membered ring will be converted into 7-membered ring. So ring expansion products, they will be formed. Some more example of ring expansion products: indene on reaction with chloroform and tertiary potassium tertiary butoxide at 0 degree centigrade. We know that potassium tertiary butoxide on reaction with chloroform will generate dichlorocarbene as the product, and that dichlorocarbene will get added to this carbon-carbon double bond to give us these types of cyclopropyl rings. And then these cyclopropyl rings, with the elimination of one of the halogen from here and hydrogen from here, will undergo ring expansion reaction to give us beta chloronaphthene as the product. And here we can say that the reason for this ring expansion is that we are generating an aromatic system as the product. Similarly, in case of heterocyclic compounds, for example, indole or pyrrole, both of these, they are heterocyclic aromatic compounds. Similar reaction can take place for ring expansion product formation. And in both the cases, you can see chloroform in presence of a base will give us dichlorocarbene, and that dichlorocarbene will add to this carbon-carbon double bond in case of indole, and this carbon-carbon double bond in case of pyrrole. And then these types of dichlorocyclopropyl derivatives, they are formed, and these derivatives, they undergo ring expansion with the removal of HCl from here, and we will get 3-chloroquinoline and 3-chloropyridine as product in both the cases. And you can see that both these products, again, they are aromatic products. Then is carbenes and carbenoids, they very easily undergo dimerization reaction, and the products of dimerization are generally alkenes. So you can see over here this type of carbene generated from these types of heterocyclic compounds. Two molecules of these carbenes, they combine to give us these types of carbon-carbon double bond formation, that is polyalkylene ethanes, they are formed as the product, and such type of equilibrium is known as Van Slyke equilibrium. Similarly, this was the example of carbenes. Similarly, in case of carbenoids, this is chromium carbonyl carbenoid formed from diazo compound of this nature, and then this can dimerize at these positions to give us these types of alkenes as the product, and ratio of E to Z product formation is 2 is to 1. If two molecules of E they are formed, then one molecule of Z will be formed. So ratio of formation of both the isomers or geometrical isomers is 2 is to 1. And then some other reactions, synthesis of allenes that will take place mostly in alpha-alpha dihalo cyclopropanes. So when alpha-alpha dihalocyclopropanes, which are formed from the reaction of alkene and the carbene, they are reacted with either sodium metal or magnesium metal in ether, then these types of cyclopropyl carbenes they are generated. And these cyclopropyl carbenes they undergo rearrangement with the ring opening to give us these types of allenes as the product. So this is a very common method for the synthesis of allenes from alkenes. Then from carbenes we can also synthesize Spiro compounds. So here again alpha-alpha dihalocyclopropanes. So these alpha-alpha dihalocyclopropanes, for example, this is alpha-alpha dibromocyclopropane formed from the reaction of cyclohexene with the dibromocarbene. And when these are reacted with a strong base like methyl lithium, then these types of carbenes they are generated, and these carbenes they add to the carbon carbon double bond to give us these types of Spiro compounds. So these Spiro compounds they can be formed from the reaction of dihalocarbenes with the alkenes. So basically these in presence of a strong base will lead to the formation of Spiro compounds. Then one example of ring contraction reaction also. So diazo bicycloketones, these types of ketones, 3-diazo bicyclo 2,2,1 heptane 2-one, when photochemical irradiation of this diazo compound in methanol is done with the removal of one molecule of nitrogen from here, this type of carbene is generated, and then this undergo rearrangement through ring opening at this place to give us these types of ketenes through ring contraction reaction, and these ketenes then undergo reaction with the solvent, that is methanol, to give us esters as the product. So overall there is a ring contraction. This ring of 4 carbon over here 4 and 5 is converted into 4 carbon. So contraction of the ring take place. Then this is very common reaction. You have done many times earlier also, that phenols when reacted with chloroform in the presence of base is converted into salicylaldehyde as the product. So this is a very common reaction which is used since you are +2. So I am not going to repeat what is the mechanism of this reaction. So these are some of the books which have been consulted for this, and in addition some internet sources have also been used for preparing this lecture. Thank you very much.